The Earth is constantly changing. One of the ways we have been able to unravel the clues of the past has been through the use of ice cores, meant to establish the chemical composition of the atmosphere from thousands of years ago, and pollen, which indicates what types of plants grew where and under what conditions. How is information about the past relevant to global challenges we face today? What do we mean by global change? What are the major issues? Why should we care? Dr. Robert Carell has been asked to provide an overview of global change issues, including the definition of global change and a description of the initiatives that are in place to understand these important natural and human-induced phenomena. Dr. Carell is the Assistant Director for Geosciences at the National Science Foundation. He is a leader in the federal effort to develop and coordinate the interagency U.S. Global Change Research Program, as well as a recognized force in establishing an international global change research agenda.
Global change really is a new piece of agenda that gets the attention not only of the scientific community, but the public at large, policymakers, and then fundamentally it becomes a partner to economic issues and national security issues. And environment becomes a third corner of this triad of public policy. It enters into a wide variety of activities of government, ranging from climate issues, biodiversity issues, but right down into agriculture and the productivity of the nation. People often ask, what is global change? If you try to define it in terms of time, you get a little sense of the kinds of things we're concerned about. Severe storms occur on the time scale of hours, or maybe a typhoon might last 24 to 36 hours, or the monsoon might last a few days. But if you move out to 2 or 3 years, or a decade, or a century, or even a millennia, the changes in the condition of living on the planet are changing slowly sometimes, and that's what we call global change. Think of warming the central United States just a little, a few degrees. The wheat belt's going to move north. If you cooled it, it would move south. And so those things are the kinds of things we're interested in because they have long-term effects. There are direct connections between the scientific evidence and the policy interests of our nation and the other nations around the world. You can really focus it down onto 3 major topical issues that right now command not only the attention of the scientific community, but the policy community. First is climate and the greenhouse warming issue. It is interesting to note that if you do what CNN and Time did recently, ask the public, do they know about the greenhouse issue? And 85% of the American public understand that there is something called greenhouse warming. The thing that is distressing is they don't know what it means, they don't know what its impact is likely to be, and that's why we in the scientific community and the education community have to join us in this partnership to try to expand our knowledge about the fundamental problems and our awareness of what this has to do with our lives. The second issue is ozone depletion. To our shock and surprise, in the mid-1980s, we began to see in satellite images that there was massive depletion of ozone taking place over the Antarctic continent. We had introduced these things called CFCs, and we thought they were totally benign. And to our surprise, they float to the high altitudes of the atmosphere and are starting to deplete the ozone layer. And these were increasing at about 1% per year. The third, it has to do with the interannual changes over 1, 2, 3, 5 years of how what we might think is weather, it's really a climatic change that produces things like drought that lasts for several years, or it produces massive wet regions as we experienced in 1981 and 1982 in the United States. And these are driven by processes which we now understand that are called the El Nino process that occurs in the Central Pacific and changes between 3 and 7 years, sometimes very strong and sometimes very weak. And when those strong changes occur, then you get these massive effects. It's interesting, as we have the privilege of working with our fellow nations, hardly a head of state doesn't understand this. I had the privilege recently of being in Uruguay in South America. I was only there for a few hours, and during that time, the president of Uruguay asked to talk specifically about these kinds of matters. And he said during that time, a president of Uruguay who doesn't understand El Nino and doesn't understand these effects is not going to be able to survive and serve his nation well, because they affect profoundly not only things over many years, but what happens today and next year and the year thereafter. And those are the sort of timescales that politicians have to live with. There are three major vehicles we have to collaborate among the nations of the world. One is the World Climate Research Program, which looks primarily at climate. Second is the International Biosphere Program, which looks at a whole host of global change issues with a strong orientation about the connection between the biological sciences, chemistry, physics, oceans, atmosphere, things of that nature, and a new program called the Human Dimensions Effort to understand how we, the inhabitants of the planet, connect into this, how our behavior drives things like climate change, biodiversity changes, and equally importantly, how those changes then feed back and affect the future of our lives. So these are some of the things that the scientist is bringing to the table to understand how the planet functions, and these are some of the issues that we're going to have to face as citizens, scientists, teachers, educators, politicians in the years ahead. It's a major issue of profound importance to every man, woman, and child.
The Earth is constantly changing. How do we determine what is natural and what is human-induced variability? It is believed that humans are now able to compete with natural forces in terms of ability to change the face of the Earth. How do models allow us to predict climatic change? What roles do the oceans and the terrestrial biosphere play in the carbon cycle? Dr. Barry Moore III is Professor of Systems Research and Director of the Institute for the Study of Earth, Oceans, and Space at the University of New Hampshire. Dr. Moore will describe some of the important issues related to natural variability, including modeling that is developed to understand and predict changes in the Earth system.
One of the important modeling activities that is going on around the world right now are models of the climate system. These are so often called general circulation models, and we use an acronym, GCMs, and you'll see in the newspaper about general circulation models, GCMs. We know that one of the primary uncertainties within these models is the role of clouds. How will the clouds of 2050 be different from the clouds of today? Will there be more clouds, less clouds, statistically, on average? Will they be higher or lower, lighter or darker? And this combination of a very important process, the so-called cloud feedback, will be one of the important determinants of what, in fact, climate we do have in 2050. And what I've been working on these last 15 or so years is a problem called the global carbon cycle, trying to understand the sources of carbon and the sinks for carbon as we observe it building up as CO2 in the atmosphere. When we think about the burning of fossil fuel, there are certain numbers that I think we can all keep in our mind, and it allows us to appreciate the scale of the CO2 problem. Right now, we as human beings are burning about 6 billion tons of carbon as carbon dioxide through the burning of fossil fuels every year. Well, there are roughly about 6 billion people on the planet. So that's about a ton of carbon per person per year. And in the United States, it's about 5 tons carbon per person per year. It's 1 billion tons. So we're something like 1/6 of the problem. The other source, other than fossil fuel, is that about a 20 to 25% source of the total CO2 added to the atmosphere by human activities is due to deforestation. The removal of large forests, turning those forests into agricultural lands. And that is contributing at about the 25% level. Our agricultural systems in the past have tilled the land so heavily that we continue to turn the soil over and bring stored carbon, organic matter, stored carbon in the soil back to the surface where it's oxidized, burned. So that oxidation has caused a loss in many industrial agricultural systems of about 50% of the soil carbon that was there before the agricultural activity. The Gulf Stream moves up the eastern part of the United States. What makes this northward flow of water particularly interesting with respect to the global carbon cycle is that it all just doesn't flow in some huge gyre up the coast of the United States and across to Europe back. That a portion of this water that moves northward also settles and goes down into ocean depths. As the water moves north, it gets colder. So that's making it more dense. Ice is forming in the most northern latitudes. As the ice forms, that leaves the salt behind. That makes it even more dense. So it's saltier and colder. It's becoming denser. But what happens in the North Atlantic is that an additional event, and that is that evaporation is greater than precipitation. More water evaporates than is replaced by rainfall. That evaporation from the ocean makes it even saltier still. The combination of those three cause the water to become dense enough such that it settles, that you have an overturning of this dense water on top moving down. That is occurring in northern cold latitudes, where the solubility, how much CO2 can dissolve into seawater, is greater. The colder the temperature, the greater the solubility of CO2 is into seawater. For instance, if you took a bottle of Coca-Cola on a hot day and you open it up, you get more fizz out than if it's kind of cool. The same thing is happening in these northern latitudes. So where it's colder, CO2 is more soluble, and in addition, you're getting the water to go down. You can think of it as just a pipeline or conveyor belt, just some huge roller coaster or conveyor belt, which has got little buckets that are picking up CO2 and then taking it into the deep ocean. So that's the way in which we're removing carbon dioxide from the atmosphere. That's one of the principal ways. And if you add to that, that generally speaking, in the northern part of the Atlantic Ocean, you're having your most intense biological activity, which is also taking CO2 out of seawater in the process of photosynthesis, just like plants on land. But those combinations of the ocean circulation, this conveyor belt, the ocean chemistry, the solubility, better in cold temperatures, and biological productivity give us a large sink for CO2 in the northern hemisphere in the Atlantic Ocean. Now, how that might change, if climate change, we simply do not know. One thing that I think that people have been concerned about when they hear about the possibility of climate change and perhaps greenhouse warming, and that is the question of the melting of the polar ice caps, or the melting of the ice that covers the Arctic Ocean. And so there are two themes that can be played out here. One theme is that if you did begin to increase the meltwater, if you began to melt the Arctic Ocean ice, that would reverse, Lynn, this pattern that we were talking about in New Hampshire, because then you would freshen the North Atlantic. Mm-hmm. You would turn the system in the reverse. And I think that's something that people can understand, is that if you begin to add fresh water to a saline dense system, that you might change the way that density was expressing and controlling the dynamics. The other thing right away is that people start saying if we're talking about melting the Arctic ice, maybe they should buy waterfront property in the White Mountains of New Hampshire or maybe here in Nebraska. But that I think there's another aspect of this sea level rise question that naturally occurs that's useful to point out. And you can use something as simple as this, where we have a thermometer with a little flask, and this thermometer could record the temperature of the water in the flask, and then we have essentially a meter that is allowing us to have some measure of how the pressure in the glass is forcing the water. And the important thing to notice about something like sea level rise is that it's not just this question of melting ice, that just the thermal expansion of the world's ocean due to the incorporation of the heat that would be associated with greenhouse warming could actually give a significant part of the rise in sea level. It's just the ocean is expanding. No more water, no melting of the polar ice caps, and something as simple as a flask. In fact, one could almost, by just pressing on the cork here, you can see the effect of changing that pressure, or we could have added a little bit of heat right here. And that pattern of just the thermal expansion, in fact, we had I think a visual, and these are often very useful to use, where you essentially take something and break it into its pieces. This is something that business people and educators are constantly doing. They say, well, how much of the problem or how much of the effect is due to such and so? Well, in this case, we see about 50% of the sea level rise could be associated with this issue of thermal expansion. And then that ties to issues like the conveyor belt. It ties to the issue of how fast the temperature, the warming would mix into the ocean. These are things people can understand, is that if the ocean is very slow in taking up that temperature, incorporating that excess heat, then there won't be much warming. If it's rather rapid, then you'll see that kind of thermal expansion. Perhaps the most profound data set that is influencing, I think, a lot of our understanding of global change, and it will reflect two things. It will reflect the natural variability, as well as you'll see a certain pattern, a certain trend in it. And that's the data set begun by David Keeling, Scripps, in about 1957, where he started taking from Mauna Loa a daily reading of the concentration of carbon dioxide, Mauna Loa being the second highest mountain in Hawaii and on the Big Island. And this very precise record of the atmospheric concentration of CO2, begun in 1957, continued all the way to this time, shows two remarkable things. And if we could have the first slide, you can see in this pattern two things. There's the first, this wave motion. That wave motion, the up and down, is tied to one of the most familiar natural variabilities that we have on the planet, and that's the seasonal cycle. The atmospheric concentration goes down. I realize it's a little bit hard to see, but you can see as it dips downward. That's in frame or in timing with the seasonal spring-summer period, where the vegetation of the planet takes carbon dioxide out of the atmosphere through the process of photosynthesis. And then it goes up in the fall and the winter when respiration, that is the oxidation, the respiring of that organic material that was formed, dominates photosynthesis. Now you might say, well, that's kind of a northern latitude point of view. Which seasonality is it? Which spring, summer? Well, it is the northern latitude, because most of the vegetation is in the northern latitude. So you see this very regular pattern of CO2 going down and then CO2 going up, and that's completely in sync with the natural variability of seasonality, the thing that is most familiar to all of human species, and in fact to a lot of life on the planet. And the other thing that you see is this very distinct trend upward. And that's the increase from about 315 parts per million in 1957 to a current value of around 360. So there we have two things. We have the natural variability, which has a certain explanation. We can probe it. And in fact, it tells us something about our planet. We see at the global scale how it is varying. And yet it's very regular. And that's, I think, an important fact for us, that we understand that pattern of variability. And the second thing is that we see a very distinct additional trend, something on top of the natural variability. And so that says something that here we can detect a signal, a human-induced signal, outside or on top of natural variability. And I think that's a good metaphor as we look at the Earth. There are certain things that we know. We know the atmospheric concentration of CO2 is increasing. And then there's certain things that we think we know. And that is that carbon dioxide, because it is a greenhouse gas, could lead to a change in the heat balance. We will trap more heat on the planet because we'll put more CO2, because there's more CO2 in the atmosphere. Then there's things we're not so sure about. And that is, well, okay, so what? How will it change? So we go from something we know to something we think we know to something we're unsure about. And I think as educators, it's going to be very important that we keep those patterns before our audiences of what we know, what we think we know, what we're unsure of. There's another thing we can do, and that is we can find ways of creating a time machine. And in fact, as we began, we saw the ice core. And I think that the ice core record will be something that will be like the Mauna Loa record. It is so valuable because it allows us to fly back into time. So from ice cores, we're able to see a certain pattern. The temperature is on the bottom, the concentration of carbon dioxide is on the top. And you see the actual almost parallel trends, so that as temperature declines, we see CO2 being lower in the atmosphere. And then as we came out of the Ice Age, 13,000 years ago, we start up again. And you see essentially the temperature rising, and you see CO2 rising. Now the question, it's chicken and egg. What is it? Is the carbon dioxide going down? Is that what led to the cooling of the planet going into glacial time? And then as the CO2 goes up, is that what led to the warming of the planet? So we have these two signals, and they're very close together. And now we're just now beginning to get enough high-resolution information from our time machine, our ice core record, which has these trapped bubbles from the atmosphere, to say, no, it looks like that the CO2 signal was an effect of the temperature change. It was an effect of it was being caused by, maybe amplified, maybe feeding back, but it was following, it was lagging the temperature change. And that's something that we have to now be concerned about, because we now are going to kind of perhaps reverse causality. We reverse cause and effect. And I think that this idea that there is a time machine that allows us to go back into the past is extremely important for educators to be able to try to communicate that.
Human activities are releasing carbon dioxide and other greenhouse gases in unprecedented quantities. It is believed that they have the potential to change the heat balance of the Earth and contribute to a global warming that could impact all living systems. Dr. Richard Gammon is a professor with joint appointments at the University of Washington School of Oceanography and the Department of Chemistry. His research has focused on some of the crucial questions related to the global carbon cycle and climatic change.
All of the climate scientists working on this problem around the world are convinced that there will be a warming. It's just a question of how warm, how fast. There is a broad agreement that the warming, by the time that the carbon dioxide has effectively doubled, which is sometime in the middle of the next century, 50 years from now, the warming will be about 1.5 to 4 degrees centigrade, or 3 to 8 degrees Fahrenheit, warmer than today. To try to put that into perspective, the natural climate variability over 100-year timescales is about 1 degree Fahrenheit, or half a degree centigrade. And the kind of warming that we experienced coming out of the last ice age was typically 4 or 5 degrees centigrade. So that the warming that's predicted for the next century, 50 years from now, is possibly comparable to the warming we experienced when we came out of the last ice age, which took several thousand years. So what if the world warms up a little bit? Well, actually, the consequences could be very important. It's clear there may be some winners and some losers, but by and large, rapid climate change, rapid warming, and changes in storm frequency, in moisture, will be largely detrimental for societies and for natural ecosystems. At risk are our agricultural systems, our fisheries, our forests, and our cities. Rapid sea level rise will impact coastal ecosystems and fisheries and forestries in the near ocean environment, where most of the world's population lives. It's possible that grain-growing areas in Canada will have an advantage, more frost-free days, and the same in Eurasia, possibly. But it's likely that the negative aspects of climate change will affect agriculture more than the positive. I want to stress that the greenhouse effect is natural, that without the natural greenhouse effect, the Earth would be a frozen ball, and we would never have recovered from that. The temperature, if you could have the Earth's atmosphere as it is now, but remove the CO2 and water vapor, the Earth would be about 30 degrees, 70 degrees Fahrenheit colder than it is now. It'd be well below freezing. The oceans would freeze solid, and the Earth would stay frozen. We know that didn't happen, so that we know that a natural greenhouse effect has kept the Earth at a habitable temperature over geological time and through the evolution of life on this planet. What we're talking about now is a possible 5 or 10% increment on this natural greenhouse effect due to the human activities, which are increasing the concentration of these heat-trapping gases. Now I'd like to stress again the things that we absolutely know for sure, that scientists are not arguing about, because I feel, and I talk to school groups and public groups, there's a great misunderstanding or lack of understanding of what the scientists are really arguing about. So let's go over the points again. 1, there is a natural greenhouse effect. It's always been here. It's due to CO2 and water vapor primarily, and without it the Earth would be frozen solid. 2, the Earth has warmed up about 1 degree Fahrenheit over the last century. This is real, this is significant. Does it prove man-made global warming? No. Is it consistent with the predictions of the models for the rate of warming? Yes. Is it also consistent with the natural variability of climate on century timescales? Yes, just barely. If the warming continues at this rate for another decade, more and more climate scientists will say they're convinced that we're in the greenhouse century. I personally feel we are already. But the majority of the climate scientists are more cautious. They're not willing to say that man-made global warming is yet apparent in the climate record. Another point is that we have measured the climate gases. We know that they're increasing, and we know that we're responsible for the increase. The CO2, the methane, the freons, the nitrous oxide are all going up. It's not natural. It's due to human activity. We can trace these gases back in time to the beginning of the Industrial Revolution and back through the last ice age in the records like we showed in the previous slide. So we know that we're responsible for the increases of these gases. We know that these gases trap heat. Therefore, other things being equal, the increase in these gases will cause global warming. None of the predictions are for cooling. None of the predictions are for no change. They all say warming. There's a range of warming in the predictions which we will come to. The average warming for the middle of the next century is about 3 degrees centigrade, or about 6 degrees Fahrenheit. This is not a lot smaller than the warming which occurred when we came out of the last ice age. It's within the range. It's as likely to be that kind of warming as it is to be something much smaller. The range is 1.5 to 4.5 degrees centigrade. That's about 3 degrees to 8 degrees Fahrenheit by the middle of the next century. And so the warming is comparable to that coming out of the last ice age, but instead of taking 2,000 years, the warming will occur in 50 or 100 years. So it's not simply the magnitude of the warming, but the rate at which the warming will occur, which will be a problem for us. Let me just make sure I get these points. CO2 has been and will be the major greenhouse gas. As we deplete the world's reserves of petroleum and natural gas, the greenhouse problem for the future will be the combustion of coal. Primarily China, Russia, and the United States have the major coal reserves. Continued high emissions of CO2 over the next decade will commit the planet to a much altered climate for centuries. So as in the case of the chlorofluorocarbon issue, which we'll talk about a little bit later, the timescale for the recovery of the atmosphere from these changes is not measured in years or decades, it's measured in century and millennia. So it really matters what we do now and the changes that we begin to make now. In order to stabilize the atmospheric concentration of CO2, and that means to stabilize the world's climate, we have to make large, net, absolute reductions in the emission of CO2 to the atmosphere. Not just hold it at the 1990 emission level, but make reductions of perhaps 60% below the 1990 level. This is hard. We're already above the 1990 level and going away. So the commitments that countries have made to reduce absolutely their CO2 emission levels will be very, very hard to do. A few points about the warming that we're quite sure of. The warming will be greater on land than over the ocean. The warming will be greater at high latitude than near the equator. The warming will be greater in the wintertime than in the summertime. What about changes in rainfall? A warmer ocean, yes, will evaporate more water. Most of this rainfall will occur over the ocean. The only way that moisture evaporated from the ocean reaches the land is on winds. In general, the circulation of the winds will be weaker, so that the mid-continental areas of North America and Eurasia in most of the climate models show summertime drying. Soil moisture goes down. This will have important consequences for agriculture, especially for grains. Sea level was discussed yesterday. I'll just say the prediction again for the end of the next century is about half a meter of sea level rise. It might only be this much. It might be much more. As Barry and Moore said, half of this sea level rise is from the expansion of the water itself of the upper ocean as the ocean warms. And the other half is largely from the melting of mountain glaciers, not the melting of polar ice caps. That's something further in the future. So these are the things that we know for sure. What are the major uncertainties? We don't really know where part of the carbon is going. Half of what we burn every year, half of the 6 billion tons of carbon, 1 ton for each person on the planet each year, half of that's missing. We think a good part is going in the ocean. Some of it may be absorbed by trees in temperate latitudes of the northern hemisphere. The missing carbon budget is an important puzzle. As one of the questions from yesterday indicated, the role of clouds. What will be the cloudiness of the greenhouse world of the future? Will it be cloudier or less cloudy? Will that enhance or mitigate the greenhouse warming? This is really a major first-order problem, the role of clouds. And finally, the role of ocean circulation. Will that conveyor belt slow down if more fresh water enters the North Atlantic? And what will that do for the climate of North America and of Europe? So the role of the oceans, the role of clouds, the role of the carbon cycle, the role of polar ice caps. These are the major outstanding research questions which scientists are working on today. They do not debate whether a warming has occurred. They do not debate whether CO2 traps heat. They do not debate whether CO2 is going up. They do not debate whether there'll be some warming. They debate how much warming there'll be and how quickly it will come to us. This is a 10-pound bag of charcoal, and this represents 2 gallons of gasoline. Each gallon of gasoline is 5 pounds of carbon. And although you can't see it, taste it, or smell it when it goes out the tailpipe of your car as you go down the freeway, the average car makes 20 miles per gallon. So if you really want to visualize the carbon spill, which your car is responsible for, imagine that instead of your tailpipe, that every 20 miles, every gallon of gas you burn, you have to roll down the window and throw a 5-pound bag of charcoal out the side of the road. After a while, the side of the road begins to look very different. And everybody else is doing the same thing. The bags break open. There's this black dust all over the place. You begin to see, visualize what it means to be burning that much carbon. And so that really is a difference. We have the Exxon Valdez oil spill. We have a major spill in the Russian Arctic at the present time. These are small. These are very small compared to the biggest oil spill, which is the successful refining, combustion, and use of fossil carbon, and the United States, especially our use of private vehicles for transportation. This is the area where we can really start. This is where, as a country, we can begin to make significant changes in our per person and our per nation use of carbon.
Another major issue of concern for life on Earth is the loss of ozone and the resulting increases in UVB radiation. The creation and destruction of the ozone layer will have natural and anthropogenic implications.
Essentially, the ozone layer evolved over geological time with the rise in atmospheric oxygen. Until about 2 billion years ago, the Earth's atmosphere had no free oxygen. Only with the evolution of green photosynthesizing oxygen-releasing plants did atmospheric oxygen increase in the Earth's atmosphere. And only at that time did the stratospheric ozone layer occur. And after the development of a stratospheric ozone layer, life was able to crawl onto the land, only with that protection. And the threat that we make now to the ozone layer with human emissions of chlorofluorocarbons is greater than any change in the ozone layer since the evolution of life. The ozone layer protects us from ultraviolet radiation. This is sunlight of a shorter wavelength, sufficient in energy to break chemical bonds, to scramble DNA, to cause cancer. A 10% ozone loss means a 20% increase in damaging UVB radiation at the ground. So in Canada, when there was 20% ozone loss, they were receiving at least 40% sudden increase in UVB cancer-causing radiation at the surface. So it's not simply wearing sunglasses or putting on sunblock. The natural world can't do that. So the threat is not just to people, it's to the entire natural world. We certainly know, beyond a reasonable doubt, that human activity has caused a decrease in stratospheric ozone. We saw the signal very clearly over the South Pole first, but now we know from satellite measurements over the last 15 years that the loss of ozone is occurring at every latitude in every season. I would regard the Montreal Protocol as an international success story in global change. We don't see a decrease yet because the lifetime is very, very long, but we do see that these gases are no longer increasing rapidly in the atmosphere, and that's very good news. If we could do that for CO2, we'd be a long way toward solving the CO2 global warming problem as well. Ozone is a special form of oxygen. It has 3 atoms, O3. It's toxic to people and to plants, and yet it's necessary. So there's a good ozone and a bad ozone. The ozone of photochemical smogs from poorly tuned automobiles is the bad ozone. We don't want it down here. It's a component of smog. The good ozone is the 90% of the ozone, which is in the stratosphere, where it filters out ultraviolet radiation up there without damaging our lungs down here. And unfortunately, human activity is making changes in both of these ozone distributions. We're creating more ozone down here where we don't want it, and more importantly, we're losing ozone up there where we really do need it. So let me first say then, having said what ozone is, a form of gas, the word ozone is actually Greek. It means to smell. It's a smelly form of oxygen. We need to talk about where the stratosphere is. It's over our heads, that's right, but we know when we go up in a mountain that the temperature goes down. If you go up high enough in the atmosphere, the temperature stops decreasing and starts increasing. That point defines the boundary between the lower atmosphere and the stratosphere. The stratosphere is that part of the atmosphere above us, 10 miles up, where the temperature increases as you go up. Why does it increase? Because of ozone. The presence of ozone creates the stratosphere. If the ozone layer goes away, the stratosphere goes away. So it's very important. The ozone loss will affect the dynamics and the circulation of the entire upper atmosphere. Okay, now what is a freon? What is a chlorofluorocarbon? This is a man-made chemical where a molecule like methane or ethane, a small hydrocarbon molecule, is stripped away of all of its hydrogen atoms and replaced with chlorine, fluorine, or bromine, halogens. And these are wonderful compounds. They're basically non-toxic. They're inert. They have good properties for air conditioners and refrigerators as aerosol propellants, as foaming agents, and they've been used in millions of pounds of these since about the 1950s. Unfortunately, these compounds have no sink in the ocean. They have no chemistry. They have no biology. They're accumulating in the atmosphere. Basically, every freon molecule, every chlorofluorocarbon molecule which has ever been made or released is still in the atmosphere. The lifetime of these chemicals is very long, 50 or 100 years. And so whatever we do will have consequences, as in the case of CO2, for generations to come. So that's why there's been a problem. I want to, again, as I did in the case of CO2, stress the things that scientists really know, that they don't argue about, that are really established, and contrast that with areas that are less well known or where the uncertainty is greater. So let me just say again, even though this is an issue where there is a very great agreement among the climate scientists, the public understanding is lagging. So let me just make these points again very clearly. The global ozone layer has become thinner and we are responsible. This is not a natural phenomenon. We know that it's thinner from satellite measurements, not just over Antarctica, but over all latitudes and all seasons. And we know that man-made chlorine carried there by the chlorofluorocarbons is the responsible agent. There are no man-made sources of these compounds. They don't come out of volcanoes. The ocean is not an important source of chlorine to the stratosphere.
No natural.
No, there are no natural sources of these compounds at all. We know that the abundance of chlorine in the stratosphere due to these gases has increased 600% since 1950. No wonder that the ozone layer is responding. There's 6 times more chlorine there than the natural level. The lifetime, as I said, is very long. It's the lifetime of these gases in the stratosphere for the sunlight to break them down. And eventually the chlorine atoms, which are involved in a cycle of ozone destruction, they rains back down out of the stratosphere. Pieces of the molecule are then lost from the stratosphere. But the lifetime of that process is very long. The loss of ozone from the stratosphere means that more ultraviolet radiation, ultraviolet UVB radiation, reaches the surface of the planet. And this radiation, we know, reduces primary productivity in the ocean and on the land of the plants. We know that it suppresses the immune system generally of all living things. We know that it can cause cataracts and lead to increased rates of skin cancer. The last point I want to make is that the connection between ozone depletion and global warming is that these chlorofluorocarbon gases are themselves potent greenhouse gases. Each molecule of chlorofluorocarbon is 10,000 times a better heat-trapping agent than each molecule of CO2. So although the abundance of the chlorofluorocarbons is low, their greenhouse action is actually quite large. Another way to put it is that one single charge of your car air conditioner freons does more damage in terms of global warming than all the tanks of gasoline you use in the entire lifetime of the car. We need to do a demonstration now to illustrate the role of a catalyst, something which can promote a chemical reaction without itself being used up. I said that the chlorine is a catalyst in the destruction of ozone. It can go around 100,000 times without being used up, but destroying ozone as it goes. So what I have here is in this jar is a bunch of cookies, animal crackers, and this is a good demonstration to do with children. And so first I'm going to have you imagine that the jar is the atmosphere, and the cookies are ozone molecules, and I don't have any sunlight, so I can't make any cookies, but I can shake the atmosphere, and you can imagine that once in a while cookies will collide and a cookie will break. That's how the cookie crumbles, right? But not very much. I'm not really breaking very many cookies. Now, this is my chlorine atom, which has been freed by sunlight from a CFC molecule. And now we'll put this catalyst into the reaction chamber. And we will again shake the cookies. And now I'm making cookie dust. The catalyst is promoting the destruction of cookies. The chlorine catalyst promotes the destruction of ozone molecules. And yet, the catalyst, I can't get it out, the catalyst is not used up. There we go. The catalyst is not used up. We have some hope that the worst ozone damage is just around the corner. That is, within the next 5 or 10 years, if international regulations hold and countries comply, this problem will stop getting worse. Does that mean the danger is over? No, we're in the period of maximum danger right now. Now and for the lifetime, our lifetime, and the lifetime of our children, the Earth's surface will be exposed to very high levels of UVB radiation. And now, by international law, a series of important chlorofluorocarbons will not be allowed to be produced or released to the atmosphere in the world from 1996 onward. And a series of substitute compounds will be introduced, and the technology for the transfer of these substitute compounds to the developing world is also facilitated by a fund to help these countries like China, Brazil, India get the substitute technology so they can have refrigerators and air conditioners like we have had. So the good news is that these regulations are working, as shown in the next slide, which is actually the measurement of the chlorofluorocarbon 11 concentration at a number of sites around the world. And at the very top of the curve, you can see that there's a leveling off, a rolling off towards steady state. This is the good news. We actually are beginning to bring these compounds to a constant level in the atmosphere. How long will it take for it to go back down? I said 50 to 100 years. And that's the time of danger for the future, for the next several generations, until these compounds have left the atmosphere. We can't go up and fill up the ozone hole. We can't go fix it. We can't squirt anything up there. We simply have to wait, cross our fingers, put on the sunblock, and hope that the natural world will also suffer through this time with us.
Ecosystems must be able to respond to climatic changes that occur in the Earth. Dr. Lisa Gromlich uses paleoecological techniques to study the interaction of vegetation. Times range from decades to millennia. We learn a great deal about the possible future and past. Information contained, for example, in tree rings. Dr. Gromlich is an associate professor in the Laboratory of Tree Ring Research and director of the Institute for the Study of Planet Earth at the University of Arizona.
When we first started celebrating Earth Day, environmental problems appeared to be fairly simple. Growing up in the Midwest on the shores of Lake Erie, for instance, we were concerned with point source pollution, and it was a relatively simple question of tracing the pollutant back into the source and looking at relatively simple sets of effects that that pollutant might have on a system. Increasingly, especially over the last decade, we've come to realize the global magnitude of human impacts, especially on atmospheric composition. We can no longer localize either the drivers of those changes, the human activities that cause those changes, or the effects of those changes. What we've discovered, in part due to the kind of climatic we've had in the last couple of decades that have the unglaciated era, was about a global temperature change of about 5 degrees Celsius. That's not unlike some of the range of estimates that we have for a future in which CO2 is doubled, something that's likely to happen within the next 50 or 100 years. What we've got in this grassland is a very, very productive system in which sunlight is captured by the grasses, photosynthesis occurs, we have the accumulation of carbon on this landscape. The rate of carbon accumulation is critical and balances the amount of CO2 that either accumulates in the atmosphere or is decreased in the atmosphere. In order to understand how CO2 will continue to change through time, we need to know something about the productivity of the ecosystem. An ecosystem is the collection of plants and animals and the physical environment in a given place or in a region. Ecotones are the transitions between one type of vegetation and animal life and another. So for example, one of the ecotones we've been looking at the field sites here is the structural changes we see when we go from a forested landscape, the relatively dense stands of oak trees, down into the broad expanses of grasses with just a few scattered juniper trees. We're interested in ecotones because when we start to see vegetation change, it is often most dramatic and most detectable at these transition zones between one type of vegetation and another type of vegetation. Now, as we go up in elevation, the climate gets a little cooler. We start to see broad fields of grasses. This is a very, very biologically rich ecosystem. As we continue up in elevation, we move into the oak woodlands, where we have 13 different species of oak growing in relatively dense stands with some grass undercover it. And then as we continue up in elevation, we actually get into a mixed conifer forest. At the very tops of the mountains, there's actually little patches of tundra. So we have a vegetation zonation that gives us a rich variety of plant life and a lot of opportunities to study the relationship between climate and plant growth. What paleoecology, the study of the distribution of plants and animals over anywhere from the last decades to the last thousands of years to the last hundreds of thousands of years, has shown us is that plant life, animal life, and climate are tightly tied together, and that when we see changes in climate, we see plant responses. As a paleoecologist, we have a number of different kinds of tools to study how vegetation has changed in the past, and they all give us different kinds of information on different time scales. When we're dealing with forest systems or the transition from a forest system to a grassland system, we have a particular challenge because we're dealing with organisms, i.e. trees, that are a whole lot bigger than us, they're a whole lot older than us. So basically, what we need to do when we study a large, long-lived organism is to use a series of techniques that allow us to look at the behavior of that organism over different parts of its life cycle. And here we use a different tool for paleoecological research. I'm a scientist that's been trained in the study of tree rings. The relative width of those rings tells us something about how climate has changed in the past. Now, one of the things that happens when climate changes is that trees have different rates of regeneration. So when we core trees, we can find the date at which it was established, and knowing something about rates of establishment through time tells us about the details of the vegetation responses to the climate changes that we see. When we core some of the smaller trees, the seedlings and saplings, what we're trying to understand there is the date of establishment and how climate variability during the 20th century has either accelerated the establishment of these small trees or deaccelerated, stopped the establishment. That kind of empirical data is well matched when we can do experiments where we actually manipulate the environment. So climate variability over the last couple of decades gives us a natural experiment, if you will. There'll be sequences of dry years and sequences of wet years. But if we really want to understand how those dry and wet years affect plant performance, we actually need to turn to an experimental approach. Now, if I can have the slide of the free air carbon experiment, we see that instead of just doing this in small bottles, it would probably be useful to think about how CO2 enhancement might affect a whole ecosystem. And this is actually a slide of an experimental setup outside of Phoenix, Arizona. That's a cotton field, and those pipes sticking out of the ground are actually emitters that are emitting CO2, maintaining that cotton field at a doubled CO2 levels. In other words, twice the amount of CO2 in the atmosphere as that would be normally experienced. What's great about this experimental setup is that the entire ecosystem is intact other than a couple of furrows that they use to put in the CO2 pipes, and that there's a sophisticated set of wind vanes and wind monitoring devices there so that they always know exactly how much CO2 to be emitting from the emitters to maintain that at a doubled CO2 level. So we have experimentation that can go from everything from looking at individual species in little glass jars or plastic bottles, whatever, to entire ecosystems that we manipulate. Now, in addition to manipulation, it's also critical to be monitoring the environment. And in the next double set of images, I want to emphasize the importance of satellite remote sensing for looking at rates of deforestation. Here we have two images of deforestation, and I think if once again you were to ask your students or the lay public that you deal with what these are pictures of, they probably would quickly both identify both these images as tropical deforestation. What you need to know is that the image on the left is actually an image taken out of Washington State and makes the point that we not only have deforestation in some of the tropical countries, but we're experiencing the same, if not greater, rates of deforestation within the Pacific Northwest and the northwestern part of North America in general. So monitoring is critical with respect to understanding rates of human impact, especially these types of land use change like conversion of forest to non-forest uses that we've been talking about. The next time you hear the word global change, which will probably be within the next hour at this conference, I want you to stop thinking only in terms of climate change and start thinking about ecological dynamics. Global change is not something that's going to happen in the future. Global change is happening now. We have an increase in CO2. Probably more importantly, we are transforming the surface of the Earth. Those transformations in the surface of the Earth are causing a loss in species and a very large change in the kinds of habitats that we see on the face of the Earth. My hope is that you're going to join with me in trying to educate people and alerting the public as to the extent to which humans are actually very involved with a series of global changes that are not controversial and are not some science fiction fantasy in the future, that they're happening right now.
The unprecedented population growth rate is contributing to depletion of natural resources and the production of waste at an alarming rate. The human dimensions of global changes requires our developing new ways of understanding complex issues. Dr. Dennis Meadows is Professor of Systems Management and Director of the Institute for Policy and Social Science Research at the University of New Hampshire. His work focuses on projects designed to clarify and implement options for sustainable development.
My mode of science is computer modeling. I create models or representations of the reality so that I can see why things behave the way they do and how we might make them behave better in the future. One of the most valuable things we can give our students is the interest and the desire and some practice in imagining what the world could look like, what their community could look like, what their family would look like in the future. One of the real problems we've had as educators in the past is our tendency to split things up into small pieces so that we can convey sort of full knowledge and mastery about individual components. But of course, the essential feature of a system like the global ecosystem is that the whole behaves in a way different from the sum of the individual parts. One of the real challenges for teachers is to begin giving our students the tools and the will to look at whole systems, to understand how damage done one place causes serious problems elsewhere and maybe much later. When you look at the longer term for the global ecosystem, you'll see that one crucial ingredient for sustainable systems is an inherent respect for nature. The natural ecosystems have a finite ability to produce, and that if we want to preserve them for the long term, we have to respect that and limit our demands, limit our harvest of the renewable resources. Because the world is an interconnected system, and when you deplete an important resource one place, or you do grave damage to the ecosystem in one place, over time, decades sometimes, those consequences ricochet into very remote parts of the system. It's useful to differentiate between two kinds of resources, renewable and non-renewable. Because the first are infinite in one way if we don't overuse them. Renewable resources regenerate. Trees grow new trees. Fish spawn new fish. Soil fertility does tend to renew itself. And if we make demands on these resources below what they can supply, they will be available to us for thousands of years, just as they have been in the past. The non-renewable resources like oil, other fossil fuels, copper, and so forth, exist in finite supply. They aren't regenerated. There is no finite usage rate which can be sustained indefinitely over all future time. We're rather talking about using it at a low enough rate that technology permits us to bring in renewable substitutes. Looking at these physical problems, we've quickly perceived that the key issue is social response. The long delays between when science is done and when the politicians, the economists, the corporate leaders, the workforce, the universities have taken that knowledge and reflected it in a new set of laws, a new set of social attitudes, new products, and so forth. We knew about the possibility for ozone depletion long ago. It's only today that we have finally implemented the laws and developed the new technologies which let us reduce production of the chlorinated fluorocarbons by below half their recent production peak levels. When it takes 50 or 70 years for populations to stabilize, when it takes 50 years to develop a new energy system after you've depleted the fossil fuels underlying your current one, when it takes 20, 30 years to change curriculum in schools and so forth, you need to look out far ahead.
Nate, I'm gonna take this one.
Social responses can't be predicated simply on where we're at today, but where we're already headed 10, 20, 30 years or so from now. That's actually one of the really big challenges for teachers, is to help their students develop a much longer term framework for assessing the costs and benefits of current actions. The world's problems have been created by 5.5 billion people getting up every morning and going about their daily life, committing billions and billions of actions, some of which cause damage and some of which don't. The only way we're going to solve these problems is if we can get those 5 or 6 billion people to get up every morning and behave in a slightly different fashion. So the blame and the responsibility all lie at the individual level. I'm reminded of a saying which was taped on the door of one of my teachers, which was, even if I knew the world would end tomorrow, I'd plant a tree today. And for me, teaching is planting a tree. It's giving our next generation the ideas and the values and the will and the enthusiasm to grapple honestly with these problems, to have the technical competence for dealing with them, and the faith that we really will be able to solve these issues. And that's why I've always thought that teaching is the most rewarding activity and the place where we have the real leverage.
We have come out of a phase of our history where growth, expansion, and increase dominated our culture, dominated our language, and came to dominate even our visions and our expectations. Now we see that that's no longer possible. We have to shift globally and locally to a phase of what we choose to call sustainable development, where these growth trends in some way stabilize and leave us with a different condition for our society. Hopefully one that will be equitable, hopefully one that will leave us with a diverse ecosystem, but it's going to be very different. History has shown us a tendency for populations to stabilize. The rich countries, like the United States, Sweden, Japan, and so forth, have gone through a historical process called the demographic transition, where over 100 or 200 years, a country shifts from having very high growth rates, or very high birth rate and death rate, to a very low birth rate and a low death rate. In the third illustration, you can see where we are globally with the demographic transition. The top part of that shaded area shows births. The bottom part of that shaded area shows deaths. 100 years ago, both were high and almost equal, so population wasn't growing very fast. And then around the turn, or about the middle of the last century, for a variety of reasons, improved health care, better sanitation, moving people to the city where services are more efficiently provided, the death rate began to fall. And just after the Second World War, the global birth rate also started to go down. Birth rate is still declining, but death rates are also declining. And you can see the gap between the two is very big. So population is growing rapidly. And what we earnestly hope is that through increased industrialization, changing social values, rising standards of material well-being around the world, we'll be able to continue bringing down the birth rate until once again we have some kind of equality between births and deaths. To put it in a nutshell, that was the essential focus of the Cairo conference. But if we trace out this evolution and assume that it's going to continue more or less along historical standards, as we can see in the next diagram, we still have a long way to go. The top curve shows the absolute number of people added to the population
each year. The shaded area shows the time that lies ahead, up to the end of the next century. So we see this little bulge in population growth between 1900 on the left and 2100 on the right. The lower curve shows how many people are being added to the rich countries. Most of the additional people will be added to the poor, and mainly in urban areas. If the curve proceeds as it is shown here, and this is the basis for most planning by the United Nations and the World Bank, we would be left with something in the vicinity of 12 or maybe even 14 billion people, almost 2.5 times as many as we have today, before the global population can finally stabilize. Those who are striving for sustainable development are hoping that we can accelerate this process and stabilize the population with only a few billion more than we have today. To achieve that will involve a kind of race with technology and the use of resources. The real question that faces us as a species these days is whether we can sustain industrial growth long enough to make everybody well enough off that population can be stabilized. There's a saying, industrialization is the best birth control. I don't know if it's the best, but it's the only one we've had so far that works across cultures. And the question for us as environmentalists is how we can sustain that industrial growth with acceptable environmental consequences. That means minimizing the damage it does to the environment and reducing its impact on renewable and non-renewable resources. One of the issues when it comes to development and to piecemeal development is this question of time horizon. The period of time within which the costs and the benefits of an action are calculated. There are many pressures in our society to have a short-term perspective. The media, the high interest rates on loans, the rapid rate of technological change, the rapid rate of migration by our citizens, all of these things militate against having a very long-term, decades-long perspective about a particular region. People who are going to only be there for 2 or 3 years want to maximize their situation over that time. They're not willing to make big sacrifices now in order for things to be better a decade or two later when they're long gone. As long as that short-term perspective dominates, there probably isn't a very good solution to the problem you're talking about, where piecemeal development causes inefficiencies for the total system of land use and transportation. It takes a vision, some sense about where we could all be 20 or 30 years from now, and then a community collective commitment towards working for that goal. It doesn't mean that everybody needs to expect they're going to be there for the next 30 years, but at least collectively they have to agree to impose on themselves certain kinds of land use codes, maybe certain kinds of financial penalties, which will make short-term actions cost a bit more when they're going to impose costs on society. Of course, I wrote a book back in 1972 called The Limits to Growth, which laid out a number of these issues, and I, at that time, wondered a lot about what was going to happen over the next 20 years. And recently, we've come back and revisited the analysis. There just came out a book called Beyond the Limits, which looks at these population and these industrial growth trends. And in preparing the second text, we reflected a lot on what's really happened over the last 20 years. Well, of course, on the one hand, the physical dimensions of the globe have practically doubled. Population, industrial output, fertilizer use, metal use, and so forth have practically doubled over that period of time. And as a consequence, the environmental problems have gotten much worse. It was easy to get a little discouraged by that until you begin to recognize some other things. I put up, just to start my comments, the exponential growth curves of population and industry, these curves that sweep upward to the right. An attribute of exponential growth is that for a long time it looks like nothing is happening. In the early years it looked like almost no growth in population was occurring at all, and then suddenly explosion. Well, not only problems grow exponentially, solutions also grow exponentially. I have the distinct impression that we, all of us in this, engaged even today in this process, are part of an exponentially growing solution set. We teach a few, they go and teach some few, they go and teach a few, and it's like a chain letter, you know, it starts to multiply imperceptibly at first. Many things have changed. The technology is becoming much better available to us. The sense of the planet as a global community through the action of satellites and the kinds of images which you see behind us here on the set have made an enormous impact over the last 20 years. The powers of communication, as evidenced by this satellite transmission, have grown enormously. So I see many things in place, and I am actually fairly optimistic that the solutions are going to explode here soon enough. From our analysis, we know that the next 20 years are going to be a period of incredible and profound change. Whenever we use our computer programs to project out the next 20 or 30 years, we find that the first 2 decades of the next century are times of drastic, I mean, profound shifts in the relationship between population, energy, and resources. A recent analysis out of Switzerland, for example, projected that oil production globally will peak out around the year 2000. Maybe it will be 2010. There'll still be a lot of oil available to us at the end of the next century, but when the curves are going down instead of going up, it's going to make a big change. So I don't know what it's going to look like. I just know it's going to be very, very different, and I know that the students we're working with now are going to be the ones who lay the foundation for dealing with it.
The U.S. Global Change Research Program has focused on attaining an understanding of the physical systems and cycles of the Earth. The application of those understandings allows humans to make better decisions and plans to improve their lifestyles. Ms. Eileen Shea is the Director of Environment and Natural Resource Programs for the Board on Global Change at the National Research Council. Her work relates to the importance of applying scientific information to daily life.
Today, we and the other countries of the world are joined together in a research program. Here in the United States, we call it the U.S. Global Change Research Program. But as you heard from Dr. Carell at the beginning of this 3-day conference, we are not alone. We are joined by thousands of scientists working together in international research programs whose goal is to provide information to people who must make decisions. We've been trying for most of our lives on this planet to understand a little bit about how the system works, how changes in how this Earth system occur, and what they mean for us and our lives here on this planet. We are still looking for the patterns of behavior that Aristotle believed we should look for. In many ways, we're looking for the same ones: patterns of temperature change, patterns of rainfall change, droughts and floods, agricultural growth, and changes in our lifestyle and our quality of life. There are benefits that we can accrue by studying the problems of greenhouse warming, of ozone depletion, of year-to-year climate change, or its cause, the El Nino Southern Oscillation. We can learn better how to plant, when to harvest. We can learn to plan better for water resource distribution and for water resource control, to manage floods, to manage droughts. We can learn better how to replace the fossil fuels that we burn as our primary source of energy with new fuels, new sources of energy that are less damaging to the environment. Human beings, we believe, are now at the stage where they can change the face of this planet on a global scale. And part of the challenge today is not just to understand how the natural system works, but how what we do affects that natural system. We believe today that environmental challenges are replacing military challenges on the level of national security.
Some of the core stuff that we're talking to Danielle about.
For centuries now, the farmers who live in a subsistence agriculture system in the northeast of Brazil have been aware that El Nino affects their lives, but unable to do anything about it. The 1986-87 El Nino produced a 30% reduction in rainfall. The farmers in Ceará had no way of knowing that this would be the case, and so they planted the same kind of seeds, they harvested at the same time, and unfortunately for them, the resulting production was 15% of average grain production. 15% of average grain production in a country on which people survive on what they grow is a dramatic change. It turns out, however, that in 1991-92, the same decrease in rainfall occurred, and yet a dramatic event occurred. 85% grain production by the same farmers in the same place with the same reduction in rainfall. Why? Because they knew it was going to happen. There was a forecast of El Nino in 91-92, and the state of Ceará, through its government, suggested to the farmers what to plant. They planted drought-resistant crops. They learned to live with this natural change in the system.
Here we have Vancouver Island and where we...
This example is, I believe, an example of why we're in this business. The scientists that you've been hearing from and the scientists that they represent are here because they believe we are on the verge of a dramatic change in the human relationship with this planet. We are in the position now to know how the system works, to take that information internally, make it part of our lives, and to act accordingly. Sustainable economic development is dependent entirely on our relationship with the environment. It is dependent on our knowing what the environment, how the environment works, knowing how we are changing the behavior of the environment, and to use that information to avoid, not only avoid crises, but to take action proactively, like the farmers in Ceará did with that information about El Nino. Education is the key to making all of the scientific results you've heard about today and over the last 2 days a reality. To take science, to transform it into information that we can understand, to communicate that education, that information through education, both formal and informal, to use that educational tool to promote stewardship of the resources on this planet, not only for ourselves, but for generations to come, and ultimately to join in a new partnership, a partnership among educators and scientists, among scientists from different disciplines, among people of different countries, and ultimately a partnership between human beings and this planet.
As Ms. Shea pointed out, the scientific community is moving in the direction of policy-relevant research. Even though the science is uncertain in some areas of global change, and we don't have definitive answers on everything, the reality is we still need to make decisions on the best information available at the time. Irrespective of whether or not you believe we're on the verge of impending environmental disaster, it only makes good sense to use resources wisely in consideration of all life on the planet. I'd like to take a few moments and summarize what was addressed in these broadcasts. Dr. Carell defined global change, gave an overview of the major issues, explained why we should be concerned, and talked about the national and international initiatives in place to study global changes. He also pointed out that every man, woman, and child will be affected by global change. Dr. Moore talked about natural variability, the carbon cycle, and the important role of the oceans in carbon sequestration. While there is natural variability, humans are contributing changes to the climate system in the scale of the natural world. Dr. Gammon discussed global warming, and that the Earth would be a frozen ball without this natural phenomenon. He talked about ozone and the unequivocal human-induced destruction occurring. He made note of the international scientific consensus of the IPCC on what we know for certain, what we think we know, and what we still need to learn. You have the IPCC report in your resource guide. You may want to take a look at it. Dr. Graumlich presented an ecologist view of global change, emphasizing the responses occurring within ecosystems now, not tomorrow. Dr. Meadows described population increases, problems in distribution and consumption of resources that result from that. He also highlighted the usefulness of simulations as an educational tool and the applicability of these concepts to all people and all nations. Ms. Shea gave us a hopeful message about policy-relevant, economically relevant, personally relevant applications of scientific research. There were a number of overarching issues that every speaker mentioned or implied. This is the first time in the history of humankind that we have the potential to irrevocably change the Earth system. To quote Tim Wirth, the economy is a wholly owned subsidiary of the environment. We have a window of opportunity to be proactive instead of just reactive to reverse some of the destructive trends that we have set in motion. The ways we can be proactive depend on two very important steps: educating ourselves and others, and taking personal responsibility for our relationship with the environment.